All right, I think I'm going. I hope everybody can see me. Welcome back. I sent an email to the whole class maybe an hour ago. I realized there was a typo in the assignment on the class website. It's fixed now, so if you look at it now, you'll see the right one. I had there were a few problems that I had forgot to put on there. So if you already did them, you didn't do the wrong ones. There's just a few more for you to do that are there now. Sorry about the mix-up. Everything's fine now. All right, so today we're going to talk about the total change theorem. The total change theorem. You know, theorem just means like a true fact that you can prove. I don't want to talk about proof. I gave some reasoning for it in the video. I hope you believe what I said, but I'm just going to tell you the punchline here is that the definite integral of a rate of change, that is f prime, if you have a derivative and you take the integral of that, the definite integral, that is the area under the curve, the area under the curve of the derivative is the total change of the original function across that interval. By that interval, I mean if you're doing the integral a to b, f prime of x dx, this is the total change in f from x equal a to x equal b. All right, this is what the book calls the total change theorem. All right. This is the meaning of the definite integral, like in a word problem. The area under the curve as a geometrical area is usually not terribly interesting in the real world because it's not all that often in the real world. You need to find the area of some weird shape, but that area under the curve actually represents something useful. If you are looking at the curve of a derivative of something, if you're looking at the derivative of something, the area under the curve of the derivative is the total change in the original function from x equal a to b. If you're doing the integral from a to b, it's the total change from a to b. All right, this is the basic idea. Let's see if we can do. I got just 2 examples to try, and then as usual for my Zooms, my strategy is on Tuesday is basically all me. On Wednesday, it's sort of half and half. I'm going to do some, and then I'll let you guys ask questions and work on the homeworks. And then Friday is sort of all you. Anyway, let's do some examples. So, for example, here's one that I made up, and then I have another one that I'm taking out of the book. So, it says, how about, this is a made-up example. I am pushing a block, say. This is a sort of a physics example. When you push something, when you apply a force to something, it causes that thing to accelerate, provided that the force is strong enough, or the thing is not blocked some way. So I'm pushing a block, and it accelerates according to this function. A of t equals, let's say, 3t plus 1. And the units of acceleration are centimeters per second squared. I don't care if you know anything about physics, but I hope you know. When you push something, it begins to accelerate. That is, it starts to move. It gains some velocity. That's what acceleration means. Okay, and this very simple function here means sort of at time 0, it's going to have one acceleration of 1 centimeters per second squared, and then the acceleration increases. All right. The only thing you need to know about from physics, and this is something that we have talked about in this class already, is that the acceleration is the derivative of velocity. All right, so I will just remind you of this fact. The acceleration tells you how quickly the velocity is changing. That's what acceleration means. So the acceleration is the derivative of the velocity. Anyway, the question for this problem is, I would like you to estimate the total change in velocity from time 1 to time 5. And I have to tell you, using rectangles on the left endpoints and n equals 4. All right, this is the whole problem. So I'm pushing a block, which makes it accelerate. I want you to estimate the total change in velocity between time 1 second to time 5 seconds, which is sort of how fast did my pushing end up speeding it up over that duration of time. All right. Since the velocity is the derivative of the acceleration, we can find this total change by doing the integral of the derivative. So we can do the total change in v will equal the integral from 1 to 5 of v prime, right? This is what the total change theorem says. The integral of the derivative is equal to the total change of the original function. But this v prime, of course, is the acceleration, which is this function, 3t plus 1 dt. All right, so we just have to do that definite integral. And we don't know how to find the actual exact value of the integral, but we're going to estimate it. That's your job in this problem. Estimate using rectangles on the left endpoints with n equals 4. So we can do it just like we did, all those examples that we did yesterday. So we begin by dividing the interval into 4 equal pieces, the interval from 1 to 5 into 4 equal pieces. I guess the points would just go 1, 2, 3, 4, 5, right? And then we are going to choose the left endpoints. So in this example, that would be these ones, right? And I think we can just write down the answer. What can anyone tell me? What's the delta x in this example?
1.
It is 1. Yeah, thank you for shouting out. It is 1. The delta x is just the width of the interval endpoints, or the width of the subintervals. You can see it's 1. Okay, I think we'll just write the answer. The answer always looks like delta x times and then something plus, it's like f of, f of the first thing plus f of the second thing plus blah, 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 plus f of the last thing. Or in this case, it's, the second to last thing because I'm doing the left endpoints. Anyway, what we get is 1. So this is actually my final answer. The total change, totat, I wrote. I have this strange condition. Often when I write the word total, I write totat. I don't know why that is. I've done that like since I was a kid. I remember doing that when I was a kid. It's like something seriously wrong with me. I write the word totat, which is not a word. We plug in, okay? We do like, f of 1 plus f of 2 plus f of 3 plus f of 4, right? That's what it is in this case. My 4 points are 1, 2, 3, and 4. Now, it's not really f. What I'm calling f in this example is this function right here, the function inside the integral sign. You should not do the antiderivative or the derivative. You just use that function exactly as is. So my answer is, 1 on the outside. You can leave that out if you want. It doesn't matter. F of 1 is 3 times 1 plus 1. Plus f of 2 is 3 times 2 plus 1 plus f of 3. 3 times 3 plus 1 plus f of 4, 3 times 4 plus 1. And that is the answer. You can put it in your calculator if you want to. I don't care about that. This one I suppose you could even do by hand if you really wanted to, but it doesn't matter. All right. Are there any questions about that one? This is a simple total change problem where they give you the equation for what you're looking at, right? They just told you. By they, I mean me. Okay. As you'll see, if you look at the homework problems from this section, they typically do not give you an equation. They either give you a graph of values, and instead of plugging into the equation, you just look up the value on the graph. Or sometimes they just give you a list of values without drawing them on a graph. So I have a book problem that I copied down. This is number 38 in my book, concerning Musk the Friendly Pit Bull. Look at that. And there's a helpful picture. This is a real picture that's really in the book. I don't know why they decided to put a picture of a dog, just because this is a problem about a dog, about a made-up dog. They put a picture of the dog next to the problem. It was actually in my book. It didn't fit right next to it. Like it's on the top of the next column. So you just have like a picture of a dog all by itself. Who am I to question the authors of our textbook? It says here is her velocity during the first 4 seconds of her romp. Okay, so in these 4 seconds, those are the velocities at each moment. And it says give 2 estimates for the total distance. So in this case, we are given, so these values are of the velocity. So we have values for like a velocity, I'll write as v of t. And what we are being asked to do is estimate the distance traveled. Now, one thing that you know about velocity is the velocity is the derivative of the distance traveled. So I'm going to say, just like the acceleration is the derivative of the velocity, it is true that the velocity, v of t, is s prime of t, where s is the distance traveled. It really is. You know, that's what velocity means. It's how fast your position is changing over time. All right. In physics, usually they use s rather than d for distance or displacement. Anyway, what we are given then are values of the derivative. We are asked to estimate the total distance traveled. We are given values of the derivative. So we can use the total change theorem here. The total distance traveled distance is it's this, right? It's the integral, and the time is during the first 4 seconds. So I would do integral from 0 to 4. Those are the time that we're talking about, and then of the s prime of t, because the total change in the distance, which is s, would be the integral of the derivative s prime. All right, and those values on the table are telling us the values of the derivative. Anyway, let's just see if we can do this. The question of like, how do I work with the table rather than a graph? And when I did the one in the video, I used a graph. Here you just have a table of numbers. It's not a big deal. Let's just try and do it. It says our job is give 2 estimates, one using the left endpoint and one using the right endpoint. All right, so let's do the left endpoint first. So I begin by writing my my little interval as usual and divide it. Now they didn't tell us how many pieces to divide this in, but since our data here that they gave us is only going, you know, according to 1, 2, 3, and 4, I think that's the only way that we could possibly divide it up in this problem. You have to divide it 1, 2, 3, 4, just because that's the information that we were given. There wasn't any other, you know, we have no more information other than those points. So in this case, again, the delta x will be 1, because that's the distance between, you know, those little subintervals. And since I'm doing the left endpoints first, I choose these 4 points, and we go the total change is approximately equal to 1 on the outside, that's the delta x, and then on the inside I'm going to say velocity here. Velocity of 0 plus velocity of 1 plus blah, blah, blah. Well, I don't need the dots, right? It's just velocity of 2 plus velocity of 3. And then what are those velocities? I wrote v here instead of s prime. You could have written s prime if you want to, but that's this function. V and s prime, they are the same. What are those velocities? What is v of 0? That's the velocity at time 0, and they give it to you. That's what these numbers are on the chart. The velocity at time 0 is 0. That's what this one means, right? The velocity at time 1 is 8. That's what the next one means, and so on. So these numbers here are 1 on the outside, 0 8, whatever they are, 13, and 17. And that's the answer. You add those numbers up. This one, I could even do this. I think it's 38. Did that in my head, right? So that's the total distance that Musk the pit bull traveled during this 4 seconds. At least this is an approximation, 38. And in fact, you know, I had the answer book. You can see 38 feet is the answer for the left endpoints. Are there any questions about how we did that? In a problem where you're given a graph, you have to sort of like look carefully to see what the y values are. Actually, this kind of setup is even easier. You just read the value straight off the chart. All right. Okay, let's do, just for the sake of doing the whole problem, that was the left endpoint. So let's do the right endpoints. I think I mentioned this in the video, but this type of problem is actually much more realistic in the real world. Usually when you're measuring things in the real world, they don't have formulas. They are just things that you're measuring, and all you get is a bunch of individual data points if you're trying to measure some, well, anything. I mean, especially like in a sort of financial business kind of setting, things don't tend to, like if you're looking at stock prices every day, they don't obey any kind of formula. They just change every day in some weird way. You don't get formulas. All you get is like lists of numbers like this. This is very realistic to how things work in the real world. And so that, like, this method that we're talking about is actually in many settings in the real world, this kind of stuff, where adding a bunch of little numbers together, is actually more useful than knowing how to do derivatives and antiderivatives of equations, because in the real world, not everything works according to equations. In physics, you got equations. Everything else, you got, you know, data. Anyway, okay, let's just finish this off. Using the right endpoints is very similar. 1, 2, 3, 4. This time I choose only these guys, right? And I do the same thing. So the total change, can I just write my answer? It's 1 times v of 1 plus v of 2 plus v of 3 plus v of 4. And then these values you get out of the chart there. It's 0. It's the same ones. 0, 8, 13. What? Sorry, it's not 0. I skipped the first one, right? The first one that I'm using in this one is 8, 13, 17, and then the last one is 18. So add those numbers up, and whatever you get, that's the answer for this little part B. All right. Any questions about that one, about those ones? Somebody asked me, I think it was about this. I hope that addressed this kind of problem.